What is a tropical cyclone? A tropical cyclone is a low-pressure system that originated in a tropical region, which is between the tropics, 23.5 degrees north and south, and excluding 0 to 5 degrees north and south due to the Coriolis force, because there's no Coriolis force at the equator. From the equator to 5 degrees north and south. Tropical cyclones form over warm water. They have organized circulation. Their main energy source is the release of latent heat. And the most intense tropical cyclones are known as hurricanes or typhoons, depending on their region. Because there are different names for hurricanes around the world. Ingredients for tropical cyclone development. Warm water temperatures of at least 80 degrees Fahrenheit or 26.5 degrees Celsius, or warmer to a depth of at least 150 feet. Oh, don't mind that, that's the printer. Rapid cooling of rising, unstable air. That's another ingredient. The next ingredient is high humidity in the lower to mid-troposphere. It needs a weather disturbance, for example, an easterly wave as a starting point. And weak upper level winds, little wind shear, because the wind shear breaks up the clouds at the top. So wind shear actually prevents it from forming as well. There's a picture here of the inside of the layers of a cyclone. So it's got the eye of the cyclone and all of the layers that are broken up into different walls. I'm not sure how to describe the hurricane exactly, except that it has the eye in the center, which has the eye is the calmest part of the storm. And then it has the eye wall, which surrounds the eye. And then it has like these chambers in between these surrounding layers of cloud walls. At least that's what it looks like on the picture here. So I'm going to read the little bubbles that talk about the components of the hurricane. We've got deep low pressure, which is deep central low pressure that draws surface air in from all directions. There's sea spray, which is rapid air inflow that whips up huge frothy ocean waves, and sea spray, which evaporates and increases the moisture content of the air, which helps to strengthen the storm. Then there's latent heat, which is inflowing air when inflowing air reaches the eye wall. As it rises, it cools to the dew point, and water vapor condenses. This condensation releases latent heat. And then finally, unstable air. Latent heat increases the instability of the rising air. This deepens the surface level low pressure as air rises faster. And then it says go back to number 1, which is deep low pressure. I think that means it repeats that cycle again. From deep low pressure, sea spray, latent heat, and unstable air. Tropical cyclone basins and naming convention. So, in the North Atlantic and Eastern Pacific, hurricanes are called hurricanes. In the Northwestern Pacific, it's called a typhoon. In Australia, or the South Pacific, it's called a willy willy or a boggio. And in the Indian Ocean, it's called a cyclone. Tropical cyclone basin formations. There are 7 tropical cyclone basins where tropical cyclones form on a regular basis. In the Atlantic Ocean, or the Atlantic Basin is in the North Atlantic Ocean, the Gulf, and the Caribbean Sea. Here, the hurricane season is officially from the 1st of June to the 30th of November. Peak activity is in early to mid-September. Once in a few years, there may be a tropical cyclone occurring in May or December. The Northeast Pacific Basin is from Mexico to about the dateline. This has a broad peak with activity beginning in late May or early June and going until late October or early November, with a peak in storminess in late August and early September. The Northwest Pacific Basin goes from the dateline to Asia, including the South China Sea. This is where tropical cyclones occur all year round, regularly, though there is a distinct minimum in February and the first half of March. The main season goes from July to November, with a peak in late August to early September. The North Indian Basin includes the Bay of Bengal and the Arabian Sea. It has a double peak of activity in May and November, though tropical cyclones are seen from April to December. The severe cyclonic storms, which are greater than 74 miles per hour or 119 km/h winds, which occur almost exclusively from April to June and again in late September to early December. The Southwest Indian Basin goes from Africa to about 100 degrees east. Beginning in late October to early November, reaching a double peak in activity, one in mid-January and one in mid-February to early March, and ending in May. The Southeast Indian Australian Basin goes from 100 degrees east to 142 degrees east. Beginning in late October to early November, reaching a double peak in activity, one in mid-January and one in mid-February to early March, and then ending in May. Kind of like the one we just covered, the Southwest Indian Basin. But the lull in February for the Australian Southeast Indian Basin is a bit more pronounced than the Southwest. Finally, there's the Australian Southwest Pacific Basin that goes from 142 east to about 120 west. It begins in late October to early November and reaches a single peak in late February to early March, and then fades out in early May. So it seems like those last three kind of have a similar schedule with some differences in strength and timing. Tropical cyclone basin formations. Okay, there's a picture here, and it has hurricanes around the world and their season dates. So we've got hurricanes from August to October, typhoons from June to December, cyclones from January to March. Now, hurricanes and typhoons, it varies a little bit by location. So the Gulf Hurricane Basin, it says from August to October, but the Pacific Hurricane Basin is from June to October. So just a couple months difference, but depending on which ocean the hurricane is from, it's either August to October or June to October. For a typhoon, if it's in the Pacific, it goes from June to December, and if it's on the other side near the Indian Ocean, it goes from June to November. Stages of hurricane development. The first stage is the tropical wave. This usually originates from North Africa and moves westward. It's referred to as easterly waves, and it's characterized by elongated areas of low pressure. It can cause thunderstorms. It's oriented north to south, and it originates in the ITCZ between 10 and 25 degrees north in latitudes. There are a couple pictures here that show, one, the easterly waves and how they move with convergence and divergence. The upper air winds go up and over this little, almost like a little mountain ridge, but it's in the air. And then the other picture has an example of how water moves in the sky. So you've got the ocean air, which evaporates up and makes the air moist. You've got precipitation, and that creates these thunderstorms. Then you've got the dry air coming down. The second stage of hurricane development is a tropical depression, which is a low-pressure system that starts to form, and you can, on a map, it looks like an enclosed isobar. It has organized circulation in the center of the thunderstorm, and central pressure begins to drop rapidly. Wind speeds, though, still remain below 39 miles per hour. The third stage of hurricane development is a tropical storm. Pressure continues to fall. The system becomes more organized and circular. Rotation begins to show an eye, which is going to be in the center, remember. Wind speeds are between 39 miles per hour and 73 miles per hour, and the system is assigned a name. So it begins to be known as Tropical Storm Isaac instead of Tropical Depression 10. And then the fourth stage of hurricane development is a hurricane. It has winds of 74 miles per hour or greater, and 5 categories based on wind speed. And it's measured, the wind speed is measured on the Saffir-Simpson hurricane wind scale. A tropical depression is between 37 and 63 kilometers an hour, or 23 to 38 miles per hour. A tropical storm is 64 to 118 kilometers an hour, or 39 to 73 miles per hour. A Category 1 hurricane is greater than 119 to 153 kilometers an hour, or 74 to 95 miles per hour. A Category 2 is 154 to 177 kilometers an hour, or 96 to 110 miles per hour. A Category 3 is 178 to 208 kilometers an hour, or 111 to 129 miles an hour. A Category 4 is 209 to 255 kilometers an hour, or which is equal to 130 to 156 miles an hour. And a Category 5 hurricane, which is the most destructive, is 252 kilometers an hour to 157 miles an hour. So those last 3 are the major hurricanes: a Cat 3, Cat 4, and Cat 5. I'm not going to read off the anticipated storm surge levels for each one, but you can look at those on the slides. How do we measure tropical cyclones? Okay. So I've looked in the book to see what it's called. The little device with a instrument package. It's called a dropsonde, and it's a cylindrical instrument package that is dropped from an aircraft and falls through the storm with a parachute, which reads all of the measurements of temperature, pressure, winds, and humidity. The next slide shows the stages of hurricane development, but in a complete picture. So it starts out as a tropical wave with a mass of thunderstorms that forms that sort of wavy pattern in the wind. Next is the tropical depression, where winds increase and a closed rotation begins because of the Coriolis force. Next is a tropical storm, where winds exceed 63 kilometers an hour, or 39 miles per hour, and the storm begins to become organized. This is where it gets a name. And finally, a hurricane, where winds exceed 119 kilometers an hour, or 74 miles per hour, and there's strongly closed rotation with well-defined rain bands. And you can see how it begins to build in the picture. Hurricane naming conventions. Hurricane naming conventions in the North Atlantic. Female names were given to Atlantic hurricanes, really tropical storms, beginning in 1953. Male names were added in 1979 by the World Meteorological Organization. And 6 name lists are rotated every so many years, every 6 years. So 2019 names will be used again in 2025, but names will be retired if the storm is especially traumatic and destructive, so that it doesn't remind people of the previous storm from the last decade or so. I'm going to skip the list of names because that's really long, but there is a list of names from 2025 to 2030 that you can check out. Distribution and paths of tropical cyclones. They start in the tropics with warm, moist air and move west within belts of trade winds. They turn as they enter the zones of the westerlies. So there are fewer in the southern hemisphere and none along the equator because there's no Coriolis effect. Tropical cyclone structure. What is the structure of a tropical cyclone? 1. Spiral rain bands, which have dense cirrus overcast and low central pressure. 2. An eye, which is characterized by a cloudless area at the center. It has calm weather, and the size averages between 20 and 40 miles in diameter. And then there's the eye wall, which is located around the eye and has the strongest winds. So a lot of people are fooled by the eye because it's calm. They think that the storm has passed by, and then they get hit by the eye wall, which is even stronger than the previous bands of the storm. Profile of a tropical cyclone. There's some pictures here. One shows a hurricane. One shows, I believe that's pressures, although it's kind of hard to see, so I'm going to skip that. And the final picture is another example of the inside of a hurricane. So we've got the eye that pulls air downward, which is a little different than your typical, it's still a low pressure, but instead of the air rising up like a low pressure typically does, it pulls the air down in the eye. So in this picture you can see the eye with pulling wind down, and you can also see spiral rain bands. There are easterly trade winds. There's surface convergence and divergence aloft with high altitude winds. The profile of a tropical cyclone again has an eye in the middle with an eye wall, and the eye wall clouds come up and then they hit the troposphere, and there's inversion. Similar to what you see with an anvil cloud, where it comes up and then it starts to go sideways in the sky because it has reached the troposphere. And the inversion spreads it out across the air aloft. Then there are rain bands past the eye wall that radiate out in layers. And then there are 3 charts with surface air pressure, surface wind speed, and rainfall intensity in correlation with this picture. So the strongest pressure gradient is right along the eye wall in this picture. Actually, I will let you look at the charts because it's very visual and I don't think I can do it service by trying to explain it all. But each of these charts corresponds with the eye wall. And you can see the rise and fall of pressure, wind speed, and rainfall intensity between each layer. I'm going to skip the 10 deadliest hurricanes to strike the continental US page because it's a very long list and it might be better to look at it. Storm tracks start off going east and are impacted by the westerlies. So we have a picture here of several famous hurricanes and the paths they took. They took the usual path of crossing over the Gulf, and then as they turn upward into the United States, they get hit by the westerlies. So what you see in the chart here is this curve. What affects the strength of tropical cyclones? Changes in water temperature, because warm water strengthens and cold water weakens. A tropical cyclone. When a tropical cyclone encounters air masses, because moist air strengthens and dry air weakens. When it encounters land, because land weakens, especially mountains. And increased vertical shear, because wind shear weakens, it spreads out the latent heat. And it tears up the upper clouds. Damages with tropical cyclones. So there's high winds, flooding, tornadoes, and heavy rainfall. Damages with tropical cyclones. A coastal storm surge is the most dangerous aspect of a tropical cyclone. So storm surge is a rise in sea level caused by strong winds and low atmospheric pressure of a hurricane. The Indian Ocean is particularly vulnerable because large populations live near the coast, and poverty makes evacuation difficult. Storm surge factors. The geometry of coast. Gentle slope and shallow water equals greater storm surge. Concave coasts and narrow bays equals higher storm surge. Storm category. So the first storm surge factor is geometry of coast, and the second storm surge factor is the storm category. So generally speaking, a high category, lower central pressure will equal a higher surge, where weak storms with a vast wind field can create still high storm surge. A third factor of storm surge is the tidal stage. So high tide equals higher storm surge. And if you have a high tide, you're more likely to, the storm surge is more likely to rise over a slope. So normally, if the storm hits at low tide, a slope in the land might keep the water from going too far up the coast, but high tide will make it more severe, and it's more likely to rise up and over a dune or even storm walls. It's more likely to go up and over and much higher. Low pressure and wind form a mound of water that is pushed on shore, which floods low-lying coastal areas. And you can see a little diagram here with a sloping beach with water where at normal high tide it would be 2 feet up the beach, but with storm surge it's 15 feet or 17 feet. Storm motion and quadrant winds. So in this picture you can see a series of arrows going around a hurricane, and that's because different sides of the hurricane have stronger and weaker winds. So the north and south side of the storm has 100-degree winds, let's say. The right quadrant has an additional 20 degrees of wind, and the left quadrant has a decreased by 20-degree winds. And by degrees, I mean miles per hour. So the right quadrant is stronger, the left quadrant is weaker. And the upper and lower quadrants, those north and south quadrants, in this example, they're 100 miles per hour. From south to east, from east to north, from north to west. It would go from south to east and increase in strength. It would go from east to north and decrease in strength by 20. And then from north to west, it would decrease another 20. So it would be 100, 120, 100, and then 80. Different quadrants of a hurricane equal different hazards and disasters. So there's a visual slide here, and basically what it's saying is that you will have different hazards depending on which side of the storm hits land, because if you remember, the right side of the right quadrant is stronger than the left side. So you will have less damage on the weaker side of the storm than on the stronger side of the storm. So it matters how the hurricane hits land. Tracking tropical storms. There's a picture here of Tropical Storm Dean, and it shows let me look at my notes real quick to see what that's called. It's called a forecast cone because they used to be cone-shaped, and then they sort of rounded them off visually over time. But here in this picture, we've got Tropical Storm Dean with a forecast cone that starts out in the Atlantic and starts to come up toward the Gulf. And we've got one more slide here. Hurricane watch and warning. So a tropical storm watch is issued when tropical storm conditions are likely to threaten an area within 48 hours. A tropical storm warning is when tropical storm conditions are expected within 36 hours or less. A hurricane watch is issued when hurricane conditions and related hazards are likely to threaten an area within 48 hours. And a hurricane warning is issued when hurricane conditions and related hazards are expected within 36 hours or less. So this is kind of similar to tornadoes, but different in the sense that tropical storms and hurricanes are a little more observable. You see them coming for a longer time and you can see their trajectory. So instead of just being based on, a tornado is based on the factors of are conditions favorable, and has a tornado actually been seen? That's the difference between a watch and a warning for a tornado. Where for hurricanes, you can see the hurricane is there. You can also predict where it's going to go. You can see its trajectory. You can see all of the factors that will influence where it's going to go. So you can predict how fast it's moving, when it will threaten an area. So instead of being just, is it there, isn't it there, it's more a matter of, when is it going to be there? So that's a little bit different. That's a difference between tornado watches, warnings, and hurricane watches and warnings. Now I'm going to read Chapter 12, Weather Forecasting. Producing a weather forecast. There are 6 steps to forecasting. 1 is collecting and assimilating weather data at the global scale. So all the weather data from around the world. 2 is quality check the collected data. So you want to make sure that the data is logical to the region it originates. For example, summer in Florida should not have snow. That's very unlikely. So if you have data that says that it snowed in Florida, you should double check that. 3 is define the maps, which we'll get to the maps later in the slides, but there are maps of different altitudes. Each map tells us something different about the atmosphere and the storm itself and the weather conditions. Also, the reason you need data at a global scale is because a lot of storms travel from one side of the world to the other. We see a lot of weather factors that are impacting the entire globe or an entire region. And so weather isn't isolated to one focused spot. It's influenced by things all over the place. And you need all of that data together to create an accurate prediction of what the weather is going to do. Step 4 is to begin the predictive/forecast phase, which is basically preparing for all the different things you'll need to do to predict it, which will be presenting the data. If you're on TV, you'll need to prepare the studio, you'll need to prepare yourself, you'll need to have everything in order, all the different components to present the forecast to the public. The 5th step is to prepare the forecast maps. Make sure that they are all ready. And step 6 is to present the forecast maps. So this is when you're really ready. You've done all the other steps, and you're about to predict the weather and present it to the public. Producing a weather forecast overview. So on the slide, there's a chart with different organizations that either collect data or present data. And at the top of that chart is the National Oceanic and Atmospheric Administration. That's NOAA. And they are the head of everything else. They are in charge. They are the ones that everyone else answers to for weather data. There are 3 branches under NOAA. The first one is National Weather Service, NWS. The second one is National Environmental Satellite Data and Information Service, NESTIS. I think that's how it's pronounced. I've never heard that one before. And the third branch says others. So that's other organizations that are involved with presenting weather data. Then the National Weather Service has branches underneath it. The National Centers for Environmental Prediction, NCEP, regional offices, so that's individual offices in different states and areas, and then others. I'm not sure what those are, but probably in the same vein of organizations that collect weather data, present weather data. And then the National Centers for Environmental Prediction have the Climate Prediction Center, CPC, the Environmental Modeling Center, EMC, the Weather Prediction Center, WPC, the National Hurricane Center, NHC, Storm Prediction Center, SPC, and others. And these are organizations that present the data. So the branches higher up, they collect the data, they analyze the data, they decide what needs to be presented to the public, and this last layer is what is where it actually gets out to people. Regional offices have forecast offices and centers. There are 122 weather forecast offices and river forecast centers. The book says that the weather forecast offices are where they produce local and regional weather forecasts, and forecasters at each WFO, Weather Forecast Office, tweak the computer-generated forecasts by using traditional forecasting techniques and knowledge of their particular forecast area to create a more accurate weather prediction. Acquiring weather data. Surface observations. So, surface observations are made by the World Meteorological Organization and weather forecasting offices. On the slide here, one is a buoy which collects weather data in the water. One is a NOAA ship, and one is a NWS forecast office. So these next couple pictures are actually similar to what we covered in one of the earlier chapters. I think chapter 1 or chapter 2, where we have the ASOS data center, data collection. which has a wind tower, all kinds of different sensors, and basically this data collection center helps gather all of the data for the temperature, the rain, atmosphere that will then get used to predict the weather later on. The second picture has a weather balloon which is released into the air at least twice a day, if I remember correctly. It doesn't say on the slide, but if I remember in my homework, I'm going to double check that real quick. Yeah, they are typically launched twice a day. So the next slide is acquiring weather data observations aloft. So again, the weather balloon. Yeah, it says weather balloons are launched twice daily at midnight and noon GMT. That is, that's Greenwich Mean Time. And a weather balloon is also called a radiosonde. And it has 3 components. It has the parachute, which is attached to the instrument package. The instrument package is the part that collects all the data, and then the weather balloon itself, which takes the instrument package up into the air and collects the weather data from the atmosphere. And it's important to wear gloves when you handle a weather balloon because the oils from our skin affect the balloon's ability to stay intact. It'll both affect the weather data and it'll pop the balloon when it gets to a certain height. Because the fewer particles are on it, the better. Weather maps, depictions of the atmosphere. So the weather maps vary by height, and the lowest one is the 850 map. Then it's 700, 500, and 300. And these are the upper air maps. .850 millibar maps are 1,500 kilometers or 1 mile above the surface, and they can help forecasters with precipitation types. And they're away from the surface, so it does not experience as much daily temperature change. On 850 maps, you can see moisture and warm cold air advection. So on an 850 map, you will see advection. So on the 850 millibar map slide about advection, it has 2 pictures. You can see the isotherms, which is cold air advection coming down, and warm air getting pushed upward, like you see in a cold front. And the second picture has an actual loaf marker, and you can see again the isotherms, the cold front, and the cold air advection and warm air. Also for 850, looking at the book here, not the slides, it says the solid lines are height contours spaced at 30-meter intervals, and the dashed lines are isotherms in degrees Celsius. Regions where the relative humidity is greater than 70% are depicted in shades of green. Areas of warm and cold air advection are showed with colored arrows. The next slide is about moisture. So here you can see the moisture in the air. The 850 map gives you one way of identifying the low pressure, based on moisture, precipitation, and advection. The 700 maps are 3 kilometers or 2 miles above the surface. And here is where you see winds, and winds are used to predict movement of thunderstorms. When air temperatures are 14 degrees Celsius or 57 degrees Fahrenheit or higher, at that level, the thunderstorms will not develop. And it is warm above high pressures, because if you remember, a high pressure on the surface is low aloft, and a low pressure at the surface is high aloft. So the 700 maps are the maps that show the air aloft with the warm low pressure above the high surface pressure. About the 700 millibar charts from the book, not the slides, it says the 700 millibar flow, which occurs about 3 kilometers above sea level, serves as the steering mechanism for ordinary thunderstorms that tend to occur in the warm summer months. Thus, winds at this level are used to predict the movement of these storms. A generally accepted rule of thumb used with 700 millibar maps is that when air temperatures are 14 degrees Celsius or 57 degrees Fahrenheit or higher at that level, thunderstorms will not develop. A warm 700 millibar layer acts as a lid that inhibits the upward movement of warm, moist surface air that might otherwise rise to generate towering cumulonimbus clouds. The warm conditions aloft are usually caused by general subsidence associated with a strong high-pressure center. So again, that's that pressure aloft is the opposite of the pressure at the surface. So if you are seeing warm air, that's the low pressure aloft, where the high pressure is at the surface. The 500 maps are 5,000 meters or 18,000 feet above the surface. They show the movement of the mid-latitude cyclone, which travels with the airflow. You can see troughs and ridges, which the troughs are low pressures and the ridges are high pressures. The high pressures are clear, dry weather. So 500 millibar maps are where you will see troughs and ridges. Troughs being the low pressures and ridges being the high pressures with clear, dry weather. Upper air maps and forecasting. Here we have a picture with isobars that show a trough and a ridge. The trough is a tightly compacted line going, in this example, it's coming down in this wave pattern. And the ridge, it's curving more upward like a mountain slope, but the bars are spaced out farther apart. So in this picture, the trough lines are closer together, and the ridge lines are farther apart. 300 and 200 millibar maps. So the 300 and 200 maps are near the top of the troposphere. This is where you see the winds and the jet stream. So once you have all of these maps, you put it all together. You analyze all the data, figure out what all this information is telling you about the storm. But basically, once you have all of the information you need, you compare the data and decide, is this storm going to strengthen? Is it going to weaken? What ingredients does it have to move or to grow or to weaken and go away? The slide for modern weather forecasting has 3 pictures of maps, 3 examples, which I won't get into. Satellites in forecasting. There are 3 main satellites used for forecasting. They are TIROS, it's spelled TIROS, TIROS-1, polar orbiting, and geostationary. Those are the 3 types of satellites. Polar orbiting satellites rotate north to south. Geostationary satellites go west and east around the Earth. So that kind of makes sense with their name. So polar orbiting orbits around the poles, and geostationary goes around west to east, the longitudes. It doesn't say anything here about the TIROS-1, but that might come up in a future slide. So let's see. Satellites in forecasting. So the geostationary operational environmental satellites, or GOES, provide visible, infrared, and water vapor images. And that's one of those geostationary satellites that go west to east around the Earth. Satellites in forecasting. Visible imagery is only available during the day, but it has higher resolution. Also, it does not really show temperature of clouds. Infrared imagery is available at day and night. It shows the temperatures of cloud tops. Higher clouds are white and usually cooler, whereas lower clouds are gray and are warmer. Qualitative versus quantitative forecasts. A qualitative forecast is observable but hard to measure and easy for the public, which basically means that it's presenting it in an easily consumable, more visual way rather than analytical, rather than precise measurements, but it isn't extremely technical, It's plain language and simple and easy for people to understand, even if they don't have the scientific background in meteorology. They can still understand what's going on. A quantitative forecast is measurable weather data. It's analytical, it's technical, it has the actual measurements, and it's more difficult if you don't have the background in in meteorology and analyzing the data and doing the math and all of those very technical things. So again, qualitative is easy for the public, consumable, understandable in a simple way. And quantitative is not as simple, but it's more precise. It's more measurable. Types of forecasts. This has a couple maps on it, but I don't remember what these maps represent, so I'm going to skip this. Types of forecasts. The three types of forecasts are short-range forecasts, which are up to 48 hours in the future and have good accuracy. Medium-range forecasts, which are between 3 to 7 days in the future and have medium accuracy. And long-range forecasts, which are beyond 7 days in the future and have low accuracy. Because it's harder to predict what a storm is going to do the further out, the longer in the future. Another type of long-range forecasts are the 30 to 90 day outlooks. So those are going to be much less accurate than a same-day forecast. Watches and warnings. Here we have a couple maps. Showing a heat watch, a heat warning, winter watches, winter warnings. Just a minute, I lost my slide here. Very similar to what you see with a tornado watch or a hurricane watch and warning. It doesn't say exactly how those are determined. So I'm going to move on from this slide, but there are different maps that show watches and warnings for different types of weather events. And that is one form of forecasting. Thermodynamic diagrams. The figure in this picture is a typical display of an upper air sounding by a radio sonde. It basically has two lines coming up. One is temperature and one is dew point. And you will need to look at it to see how it's formatted and how it works. But this is called a skew-T diagram, and this helps meteorologists see the temperature and dew point vertically in the atmosphere. And one of the things you will see in this picture is that the temperature and dew point come up the chart separately, but they meet at some point and are merged together for a while, and then they separate again. And the reason why that's important is because when the temperature and the dew point are the same, that's when you have precipitation. That's when you have your clouds. And so this gives you a visual representation of when temperature and dew point are together, when they are the same. Thermodynamic diagrams part 2, because there are 2 slides to this. The figure on the right is also a skew T. Skew T's are useful for assessing the potential for instability that can lead to deep atmospheric convection. The yellow area between the temperature and dew point represents the amount of energy available for a storm. Larger areas can mean stronger storms. So another thing that a skew T map can have is it can show potential energy that supports a storm. And our final slide is forecast accuracy. So here we have a chart with local TV meteorologists on one line, the Weather Channel on one line, the National Weather Service on one line, and a baseline of perfection. That's basically exactly how the weather is. And this is a chart for the accuracy of 3 weather forecasting services. So the National Weather Service starts out very close to that perfect line, that ideal prediction of what actually happens. And then at some point it starts to waver a little. It starts to not be so accurate. And it kind of, but it is fairly close, but you can see the further out it goes, the less accurate it is. The Weather Channel starts out a little farther from the perfect line, but then gets closer as the chart goes up. So, and the graph is also showing on one line the predicted probability of rain versus the actual observed frequency of rain. So, for visual reference, when you look at it, you will see if the forecasting service line is above the line of perfect, that means that they over predicted the rain. And if the chart line is below the perfect line, it means they under predicted the rain. But generally, the National Weather Service was fairly accurate. The National Weather Channel had some trouble in the beginning, but became more accurate as time went on. The local TV meteorologist was much more inaccurate. They predicted much more rain than the actual observed frequency of rain. So that chart shows what each of those weather forecasting services predicted for rainfall and how accurate they actually were. The National Weather Service is more accurate because they have localized state data. They have data centers in each state that tells them the weather in that region. Another thing, this is the last slide, but I wanted to mention a couple examples of qualitative versus quantitative data. Qualitative would be it's going to rain, there's heavy rain, etc. Where quantitative would be there's 3 feet of rain. So in qualitative, people just want to know that there will be rain. They want to know if there will be a lot of rain. They want to know if there's just a little drizzle of rain. But with quantitative data, that's when you want a precise number. It's not just we had a lot of rain. It's we had 10 inches of rain. Or 3 feet of rain. Or it's we had so many feet of rain. And with experience, you understand how much rain is a lot of rain. But the average person who might not have experience with rain measurements, water measurements, they might not just off the top of their head know how much rain is a lot of rain. So qualitative data would be just saying that there is rain. It's a lot. So, Chapter 13, Air Pollution. The sources of primary pollutants. There are 2 categories. There are natural pollutants and human pollutants, causes that are created by humans. So, of the natural pollutants, there are volcanoes, breaking seas, pollens, terpenes, wildflowers would make pollen, wildfires, creating ash and smoke in the air, blowing dust, and bacteria and viruses. Now, these last 3, wildflowers, dust, and bacteria and viruses, are accentuated by humans. They're made worse by humans. For example, wildfires are natural, but they can also be human caused. If a human starts a fire and it spreads and becomes a wildfire, that is caused by a human. Versus a lightning strike, which would be natural, or a volcano causing a fire, which would be natural, they can also be caused by humans or made worse by humans. Now, in the created by humans category, we have combustion processes, chemical processes, nuclear or atomic processes, roasting, heating, and refining processes, mining, quarrying, and farming. The next slide has some pictures of different forms of pollution and an example of a satellite image where you can actually see the pollution on a satellite image. There's also a picture of some industry, what are they called? Smokestacks, I think, where it's billowing out fumes and smoke and stuff. Similar to what they have over in Chemical Valley. And it's got a picture of wildfires, which cause like smoke, ash, and even burning of chemicals like plastic or whatever it is that catches on fire besides just wood smoke that releases chemicals into the air. Those would also be pollutants. Sources and types of air pollution. So we've got a little diagram here where carbon monoxide is the greatest pollutant on this chart at over half, 55.1 million tons. Nitrogen oxides, which are 12.3 million tons. Volatile organics, which are 14.2 million tons. Sulfur dioxide, which is 4.9 million tons. And particulates, which are 3.6 million tons. It says here percentages are calculated on the basis of weight. 6 major air pollutants. So the 6 major air pollutants monitored by the EPA include particulate matter, which is PM, sulfur dioxide, which is SO, nitrogen oxides, which are NO, carbon monoxide, which is CO, lead, which is PB, and ground level ozone. Because if you remember from the previous chapters, ozone in the sky is alright, it's good, we need that up there to filter out the sun's rays, but when it's down here in the troposphere, it's not so great. And there's a picture here of how small different types of pollutants can be compared to a human hair. And the human hair is massive in comparison to particulate matter, which is very, very tiny. And it's very tiny in comparison to a grain of sand. This one particulate matter in the picture looks just like a little dot on the page. Carbon monoxide. Although carbon monoxide output varies seasonally, the trend has shown a steady decline from 2000 to 2014. Lead and smog. Lead is very dangerous because it accumulates in the blood, bones, and soft tissues. It can impair the functioning of many organs. Smog is air pollution in urban and industrial areas. Ozone and photochemical smog. Ozone, in addition to various nitrogen-based irritants, is a major component of photochemical smog. There is a little picture here of all of the different factors of photochemical smog, but I'm going to skip that for the moment. Volcanic smog, or VOG, is it's actually a natural form of smog. It's created when sulfur dioxide from a volcano combines with oxygen and water vapor in the atmosphere. And there's a picture here from NASA's Terra satellite where on December 9th, 2009, the Kilauea volcano on Hawaii caused a VOG haze over the islands. There's trends in air quality. There's a graph here that shows levels of sulfur dioxide, nitrogen oxides, and volcanic organic compounds, or VOC, which I won't explain in depth. In 1970, there was a Clean Air Act establishing standards. Today, 5 primary pollutants and ozone are covered by the National Ambient Air Quality Standards. And there's a chart here that explains the standard values of each pollutant. And it shows the highest level that can be tolerated by humans without noticeable ill effects, minus a 10 to 50% margin for safety. And that's because different people can tolerate different levels of pollutants. So there needs to be a reduction of the level just in case there's a person who, just in case the person measured has a higher level of tolerance than somebody else who may be greater affected by a comparatively safe amount of the pollutant. So I won't read off the whole chart, but for example, carbon monoxide has an 8-hour average of 9 parts per million and a 1-hour average of 35 parts per million. So the reason there are 2 different averages is because some chemicals you can tolerate them for a short amount of time, but not a long amount of time. So it factors in how much time you can tolerate at a certain parts per million. So in the case of carbon monoxide, you could tolerate a high amount of it comparatively. You could tolerate 35 parts per million for an hour. But you could not tolerate 35 parts per million for 8 hours. You could only tolerate 9. Air Quality Index. The Air Quality Index, the AQI, is a standardized indicator for reporting daily air quality to the general public. It provides information on what health effects people might experience within a few hours or days of breathing polluted air. Meteorological factors affecting air pollution. So there's a picture here of a factory creating pollution, and one picture has a wind speed of 5 degrees, or 5, I think that's miles a second, and the second one shows wind at 10, at a speed of 10. So in the 5 speed picture, the pollutants, the smog is very dense, and it blocks out, it is hitting the neighboring city in the distance with a very thick, dark cloud. Where in the second picture, with a speed of 10, there's still a cloud hitting the city in the distance, but it's a little thinner, not as dense. Because the wind speed dilutes the pollutants and moves them, it spreads them out so that it isn't focused in one area. And that makes it a little more tolerable. The role of atmospheric stability. Atmospheric stability determines the extent to which vertical airflow will mix the pollution with cleaner air above. This correlates with what I was just explaining with the 2 pictures, the 5 wind speed and the 10 wind speed. The vertical distance between the Earth's surface and the height to which convection will carry pollution is called the mixing depth. The greater the mixing depth, the greater the air quality. Basically, you want pollution to spread out and dilute itself into the clean air. And the next few slides are going to explain what that means, the mixing depth, and how that works. So, stable versus unstable. When air is stable, convectional motions are suppressed and mixing depths are small. Instability promotes vertical air movements and greater mixing depths. This is where instability in the air is actually good because it moves the air around, spreads out the pollution a little more. This next slide shows inversions again and how that relates to pollution. So I'm going to read the text here. Many extensive and long-lived air pollution episodes are linked to temperature inversions that develop in association with the sinking air that characterizes centers of high air pressure. So there's two pictures here. One shows these factory funnels producing clouds, and at night there is a temperature inversion in this first picture because basically two different temperatures of air are creating a barrier so that the air below does not go up into the atmosphere. But in the daytime, in the second picture, the air is able to rise up farther into the atmosphere, and this dilutes the amount of pollutants because it's able to rise up and out. So a higher mixing depth is when the air is able to rise up into the atmosphere and move around and dilute itself. And a lower mixing depth is when the pollution is trapped in a space at a certain height and it's more condensed. Here's another picture. I'll read the text first. The turbulent surface zone does not subside as much. Thus, an inversion often forms between the lower turbulent zone and the subsiding layers above. Now, I missed a slide here. I missed the pictures in it. So the stable versus unstable slide has this little picture of a curve. And at the top of the curve is an unstable marker. At the bottom is a stable marker. And basically these are marking out where on this chart the mixing depth is. So unstable air will take the pollution up higher than stable air. And then there's also a neutral line where it's sort of a middle ground. It's not stable, it's not unstable, it's just neutral. And then the bottom picture shows how that relates to the clouds, with unstable clouds rising up higher than stable clouds, which are sinking down and stuck lower in the atmosphere. Serious pollution issues. There are two pictures here. The first one is a satellite image that shows high levels of aerosols associated with the October 2010 air pollution episode in China. And you can see that it has the aerosol index has a range from white to red, and it's very densely red here in this map, red and yellow. Then the second picture is a satellite image from October 8th, 2010, which shows the pollution. It looks almost like a big cloud, and it's actually pollution. Weather safety with pollution. To protect yourself on days with high particulate concentrations in the air, wear a surgical mask if you must be outdoors, wear reading glasses, not contact lenses, and use caution when driving. Acid precipitation. Rain is naturally acidic. It is slightly acidic. When carbon dioxide from the atmosphere is dissolved by a raindrop, it becomes weak carbonic acid. Small amounts of other naturally occurring acids also contribute to the acidity of precipitation. Effects of acid precipitation. Destruction to forests, plants, and roots because they can't always handle a high pH, high acid content. Wear on statues and monuments because especially metal doesn't react well to acid. Different materials don't react well to acid, and it wears down on them over time. It can discolor them, it can break them down. And then lake contamination. I think that's the last of my slides. I think that's the last slide. That was actually the last slide. I'm going to look real quick if I have any notes about acid precipitation. I do have one note here. Acid precipitation destroys forests, plants, and roots, wears on statues and monuments, particularly copper, and contaminates lakes. And the Northeast has a lot of acid rain due to industry. So, that is all for Chapter 13. Now for the Chapter 15 slides on world climates. Early climate classification. An early attempt at climate classification by the Greeks divided each hemisphere into 3 zones: torrid, temperate, and frigid. There's a picture here of the Earth divided into 3 sections. So, the middle of the Earth, between the Tropic of Cancer and the Tropic of Capricorn, is the torrid zone. So that includes the equator. From above the Tropic of Cancer and below the Tropic of Capricorn, from the tropics to the poles, just below the poles is the temperate zone. And then the poles themselves, in the Arctic Circle and the Antarctic Circle, are the frigid zones. Now this is sort of a very primitive, simplified classification that we have learned is much more complicated now, but that is how the Greeks first classified the climate. The Köppen classification system. I'm not sure how that's pronounced, but it's Koppen. And the O has those two little dots above it. I don't remember what those are called. So this classification system is more modern, and it has A, B, C, D, and E climates. A climates are the humid tropical climates. These are winterless climates with all months having a mean temperature above 18 degrees Celsius or 64 degrees Fahrenheit. B climates are dry climates. These are climates where evaporation exceeds precipitation, resulting in a moisture deficiency. C climates are mild mid-latitude climates. Climates where average temperature of the coldest month is below 18 degrees Celsius, 64 degrees Fahrenheit, but above 3 degrees Celsius, or actually minus 3 degrees Celsius, or 27 degrees Fahrenheit. D climates are mid-latitude climates with severe winters. So D and C climates are similar, but D climates have severe winters. D climates are where the average temperature of the coldest month is below minus 13 degrees Celsius, 27 degrees Fahrenheit, and the warmest monthly mean exceeds 10 degrees Celsius or 50 degrees Fahrenheit. And then E climates are polar climates. Summerless climates, where the average temperature of the warmest month is below 10 degrees Celsius or 50 degrees Fahrenheit. Not on this chart are H climates, and we haven't covered those yet. So, but keep in mind that there is another climate called the H climate, but it isn't here on this chart, and that comes in later. There's a list on the next page that has information about each climate, but the text is kind of small. Even when I zoom it in, it gets fuzzy. So I'm going to skip this one. I think this might also be in the book. I think all of this is covered on the other slides, though. This is just a summary of the climates. Polar climates, or E climates. Lands beyond the Arctic and Antarctic circles. Polar climates are high latitude. Their climate symbol is E. It says temperature, warmest month, coldest month, and seasonal distribution. But it doesn't say what the warmest month is or coldest month. So I'm not sure where that is going. It says, locate the Arctic and Antarctic oceans. Which ocean is best identified by boundaries formed by continents? What are the 3 continents? Which ocean surrounds the continents? So those are some questions to think about. There are pictures here of polar bears, and penguins. We mentioned in class, are there polar bears on both poles, and how do you tell the difference? And something I had heard is that Arctic means bears and Antarctic means no bears. So that's something to think about, is that the name of the polar region actually tells you if there's bears or no bears. If I remember correctly, there's only penguins on one pole, too. I think penguins are at the South Pole. Don't quote me on that, but if I remember correctly. Polar climate tundra. That's ET. E for the polar climate and T for tundra. These are lands beyond the Arctic Circle. Temperatures and the land. Colder summer temperatures cause the size, abundance, productivity, and variety of plants to decrease. So there are less plants because of the colder temperatures. A periglacial landscape with ground ice and permafrost. Peripheral edges of North America and Eurasia. The vegetation is mosses, lichens, dwarf shrubs, stuff that grows close to the ground. The insects prevalent are mosquitoes and black flies. E-climates only occur, or the ET, I should say, only occurs in the northern hemisphere and a portion of the Antarctic Peninsula. Vast stores of carbon and methane are released to the atmosphere, adding to the greenhouse gas problem. That's a quote from Christopherson in the corner. Polar climate with the polar climate ice cap. That's EF. An ice cap is a sheet of continuous ice covering an extensive region. The ice covering remains throughout the year. So the precipitation is less than 10. Vegetation is no trees and stuff that mostly grows on rocks. So like moss and lichen and that kind of stuff. This area is dominated by permanent ice and snow. It is the freshwater repository for life on Earth. The Antarctic ice itself is the largest reserve of fresh water. Daily weather is dominated by dry, frigid air masses. And the major world regions are the North Pole, Greenland, Antarctica, and the South Pole. Barrow, Alaska. Utqiagvik, I think I pronounced that right, or maybe not, also known as Barrow, Alaska, is located on the Chukchi Sea at the southern edge of the Arctic Ocean. It is one of the largest Eskimo settlements in Alaska. It is the farthest northern community in the U.S., and this extreme location means that daylight extremes are experienced. Daylight of 24 hours happens between mid-May and early August. So the average temperatures, there's a chart here with average temperatures and average precipitation month by month. And I won't read that off because it's a lot of numbers to process, but you can look at it. I will read off like their January and August because those seem to be some of their. December and January are their lowest average temperatures, and August is their highest average temperature. So January has minus 1.7 degrees Celsius in January. December has minus 1.5 degrees Celsius, and August has 2.7 degrees Celsius. So that is the temperature variance. It goes from like 1.5 to 2.7. Although in October it says 0.5. Oh, but that's not a negative number. Their precipitation, their lowest number is in the winter as well. From December to March, their average precipitation is 4, and their highest precipitation, which is also in August, is 25. Climatic classification. So these are the steps for climatic classification. Step 1. Divide the calendar year into 2 6-month periods, from April to September and October to March. Step 2. Establish the season and therefore the hemisphere for each set of temperatures. And the reason you establish the season is because different seasons happen at different times of the year in the northern hemisphere and southern hemisphere. So you can compare the temperatures. If you're seeing winter when it should be summer here, then it's the southern hemisphere, and vice versa. So you can rule out half of the Earth's, more than half the Earth in some cases, because the northern hemisphere has more landmass than the southern hemisphere. But you can rule out half the planet just by knowing what season happens when. Step 3. Check for an E-climate. Is the warmest month less than 10 degrees Celsius? If yes, it's an E-climate. If not, go to step 4. If it is an E-climate, check if the warmest month is greater than 0 degrees Celsius. If yes, the climate is ET tundra. If the warmest month is less than 0 degrees Celsius, then the climate is EF ice cap. Where is step 4 here? Oh, there's a note. Low temperature takes precedence over low precipitation. Any place with all months below 10 degrees Celsius is classified as an E-climate, regardless of the precipitation amount. On this slide, we've got step 1 and 2 shown with the calendar year. So there's a chart with all of the average temperatures and precipitation from January to December. And the first step is to divide the calendar year into 2 6-month periods, from April to September and October to March. And basically what you can do is just draw a line between March and April and between September and October, and that divides the chart into, it looks like 3 sections, but because the seasons are separated into, you know how it's like the school year where the winter season goes from last year to this year. So, or really just the winter season in general, not just the school. But so you've divided up your calendar into 2 seasons, but it looks like 3 sections because of the winter season wraparound. Then you establish the season and therefore the hemisphere for each set of temperatures. So in this chart, which looks like the Barrow, Alaska one, let me see. Yeah, in this example it's the Barrow, Alaska one, and you can tell because July is 1.4 degrees Celsius on average, and January is minus 1.7 degrees Celsius, and this tells you a couple things. One, it's very cold. It matches Barrow, Alaska, but it also tells you that the warmest month is in summer, in our northern hemisphere summer. So we know that this location, even if we didn't know it was Barrow, Alaska, we would know that it is in the northern hemisphere. Step 3, now check for E climate. Is the warmest month less than 10 degrees Celsius? If yes, it's an E climate. If not, go to step 4. If it is E, then check if the warmest month is greater than 0 degrees. If yes, the climate is ET tundra. If the warmest month is less than 0 degrees Celsius, then the climate is EF ice cap. So something to think about is 0 degrees Celsius is freezing. So if the warmest month is always freezing, it's always going to have ice, because they never have temperatures to melt the ice. Step 3. Oh, yeah, it's just another slide with step 3, but it does show a chart comparing the average temperature, which I'll skip because it's really more of a visual. So this chart, there's a little thing in the corner for an example. It says the warmest month is 2.7 degrees Celsius. Therefore, the warmest month is less than 10 degrees Celsius. So this is an E climate. So the little chart on step 3 is an E climate. The next slide says, well done, but we're not done yet. So let's keep going. Arid climates, B climates. So B climates are dry climates. They lack moisture. BWH and BWK, which are the latitudinal deserts, between 0 millimeters and 25.4 millimeters. So there's a lot going on this picture, but I also know that this will all be covered on the next slides, and it'll be easier to read there. So I'm going to head over to the next slide here. Dry climates are characterized best by their lack of moisture. Where are these dry areas concentrated? What are the natural causes, not human inducements to climate change? A true desert will have less than 254 millimeters of precipitation in a year. Caution: in doing step-by-step climate analysis and calculating the value of R, the boundary between wet and dry climates hovers near 482.6 millimeters of annual precipitation. Concentrations: along tropics of Cancer and Capricorn, in a 10 degrees to 15 degree band, in influence of high pressure. That says 10 degrees to minus 15 degrees. Continental interiors. So, for example, there's a picture here of South America, which has this curve on the left side of the landmass, which makes this little continental interior, which is a good place for a B climate to be. Causes are wind direction, high pressure, cold ocean currents, and rain shadow. So rain shadow, I learned what this is with my rain bucket. So I have a rain bucket, and you can't put it underneath any trees, because the trees will hold on to water when it rains, and then when the wind blows, they will dump the water onto the ground and into the bucket. So it looks like it has rained, when realistically the sky has not rained, the tree rained. The tree held on to water, or something held on to water, and it dumped it into the bucket to give a false reading. And that's what rain shadow is. Arid climates. I'm going to make some coffee before I read any more, because this early morning air is not helping me read. Alright. Arid climates. So there's BWH, which is a low latitude desert that is hot. A BSH, which is a low latitude steppe that is hot, which in a minute we'll get to what a steppe is. A BWK, which is middle latitude desert and cold, and BSK, which is middle latitude steppe and cold. So one way to remember that is the H at the end is for hot, and the K at the end is for middle. H for hot is pretty logical. K for middle, I don't know. Maybe the K has a little a line in the middle. It looks like a little kicking person. I don't know. But if you can remember that H is hot, then rule out K. K is in the middle. And also K is cold. Hey, that there. K for cold. Alright. A steppe, in the context of a climate, is an area that is considered to be dry, but that is considered too dry to support a forest, but too moist to be a desert. Steppe land areas are primarily found in southeastern Europe and Siberia. These are grasslands that support grazing animals, and in history the peoples who migrated followed the animals, who followed the rains. So an example of a savanna, or an example of a steppe would be like the savanna. Like in Disney's Lion King, you could watch the Lion King and see a steppe in the savanna. Cold desserts, like ice cream. No, it's cold deserts. Where is a cold desert? Precipitation in a true desert, by definition, has 25.4 millimeters or less of moisture in a year. So, very dry. So deserts are not defined by being hot or being cold, they're defined by dryness. Review of bee climates and classification. Williston, North Dakota. Let's see. We already know that's in the northern hemisphere. But their warmest month, let's see, looks to be in July with 21.2 degrees Celsius. And their coldest month is over here in January, which is minus 11.7 degrees Celsius. So it's not an e-climate. I think we're going to go through the steps here to figure out what kind of climate it is. So step 1 is to divide the year into 2 6-month periods. So we've got summer and winter. Establish the season and therefore the hemisphere for each set of temperatures. We already know that the warmest month is in the summer, coldest month is in the winter. Spring and fall are kind of cut into here, but summer and winter are the defining month or defining seasons for the calendar. Now check for e-climate. Is the warmest month less than 10 degrees Celsius? If yes, it's an e-climate, but it's not because these are the same numbers for Williston, North Dakota. And summer is right in the middle of the calendar where it should be for us in the Northern Hemisphere. Temperature takes precedence over low precipitation. Any place with all months below 50 degrees Fahrenheit, 50 degrees, That's different than what it said on the other slide. That can't be right. That's 10 degrees. Regardless of the precipitation amount. I've got to go back and check now. Is the warmest month less than 10 degrees Celsius? Yeah, that's just a typo. So if you see that, that should be 10 degrees, not 50. Oh, 50 degrees Fahrenheit. There we go. So 10 degrees Celsius, 50 degrees Fahrenheit. I see my mistake there. Not a typo. That was my mistake. Let's see. Although maybe you'll be able to remember 10 degrees Celsius and 50 degrees Fahrenheit. Ah, maybe it was a good mistake. Alright. Yes, we know that the warmest month is above 10 degrees Celsius. If the climate is not E, then determine the precipitation boundary R between the dry climates. So B and the humid climates A, C, and D is what we're trying to figure out. Which of these climates is our climate? It is at this point where only one of the three equations below will be used to solve for R. Summer precipitation concentration. Wettest summer month is at least 10 times greater than the driest summer month, or driest winter month. Winter precipitation concentration. Wettest winter month is at least 3 times greater than the driest summer month. If there is neither summer nor winter concentration of precipitation, I think that's when the precipitation kind of flatlines. Everything's roughly the same every month, the precipitation levels. I think at that point you can pretty much rule out a D climate, because D climate has severe weather, it has severe precipitation. So I think you could rule that out there, but if there is neither summer nor winter concentration, then there's another math formula to use. And I'm not going to read off all the math formula because I'm terrible with math terminology. I forget it all the time. So I see all the symbols, but I'm not even going to try to attempt those. I will get them wrong. After determining R, you go to step 5. Okay. So T equals mean annual temperature, and A equals the total annual precipitation. A mean is the same as an average. So it's the average temperature is T. T is at this point where only one of the three equations will be used to solve for R. Well, this seems to be a similar slide with the same material. Summer precipitation concentration, winter precipitation concentration. Okay. To get T, you need to take the average of all the monthly average temperatures. You do this by adding all of the monthly temperatures, then divide them by 12, which is the number of months. Because to get an average, you add up all of your numbers, and then you divide it by the number of numbers you have. So we have 12 numbers because we have 12 months. So it's the combination of all the average temperatures times 12. So in this example, February is the driest winter month with 10.2 millimeters. And I think it looks like it's between June and July. But I think that's maybe June, maybe July. Wettest summer month is 63.5. Okay, June and July are both the wettest summer months because they have 63.5 millimeters of precipitation. So they're tied. So the driest winter month is 10.2. There's a little math equation here. It says 10.2 times 10 equals 102 millimeters. 63.5 is not 10 times greater than 10.2. So the wettest summer month, 63.5 millimeters, and the driest winter month, 10.2 millimeters, means the wettest summer month is not 10 times greater than the driest winter month. So we go on to the next equation. Winter precipitation concentration. Let's see. The driest summer month is 25.4 millimeters. That's April. And October is the wettest winter month, 22.6 millimeters. The wettest winter month at 22.6 millimeters is not greater than 3 times the driest winter month, 25.4 millimeters. So, alright, I think I'm starting to understand something here. So, the summer precipitation concentration equation is where we are trying to see if the wettest summer month is at least 10 times greater than the driest summer month. That's the summer precipitation concentration. And the winter precipitation concentration, we are trying to see if the wettest winter month is at least 3 times greater than the driest summer month. So in this case, the wettest summer month is not greater than 3 times the driest summer month. Which means we have neither the summer nor winter concentration. So if you have a summer precipitation concentration, there is a formula for R that is different than if there's winter precipitation concentration. That's a different formula. And if you have neither summer nor winter concentration, that's a third formula. They're not exceptionally different. I will try to read them off. So for summer, R equals parentheses 0.44 T, that's the average temperature, is T, minus 3.0. The winter precipitation is similar, R equals parentheses 0.44 T minus 14.0. And if you have neither summer nor winter concentration, R equals parentheses 0.44 T plus 13.06. So the only variable that changes is whether you add or subtract and what this number you add or subtract is. And so you use these formulas depending on the situation to figure out what R should be. And once you determine R, you go to step 5. Winter precipitation concentration. So that's that R equals 0.44 T minus 14. When the wettest winter month is at least 3 times greater than the driest summer month. There are several steps to this equation that I am not going to read off. Actually, no, I'm going to try and read this off. I'm going to try. So we have the equation for R, which for some reason it has the non-winter or summer equation. I think because in our previous example, we determined that it wasn't summer or winter precipitation. So that means it's plus 13.6. Even though it says winter precipitation up here, I think that's just there. I don't think that's related to this problem. So the average temperature we found earlier, that's the average of all of the months on the calendar, is 5.3. So we insert the value of T. So inside the parentheses, we put, we replace T with another set of parentheses, 5.3. So, and then we add 13.6. Multiply 0.44 by 5.3. That's how we solve this parentheses problem. 0.44 times 5.3. That's your T average that we found earlier. So we get a number of, we get the answer 2.332 plus 13.6. Then you add to solve the equation. So that 2.332 plus 13.06 equals 15.392. That 15.392 is your R. Then you convert R to millimeters. I'm not sure where the second number comes from, but R equals 15.392 times 25.4, which equals 390.96 millimeters, I think. Yep. So R equals 390.96. And that's a very rough explanation of the equation. And the toughest part of this is the parentheses, 0.44 T, and it explains how to do that. So if you're confused, look at the slide. It'll explain it visually. And the number that changes depending on what kind of precipitation you have on your chart is this second part, which isn't as difficult. It's just addition or subtraction. All right, step 5. Now check for a B climate. It is not a B climate if the total annual precipitation is greater than R. Because if we remember, B climates are dry, so they can't have a lot of precipitation. So on this slide, the precipitation is added together for a total of 365.76. So A represents this total. A equals 365.76. And that is the total amount of precipitation in the entire year. And it's important because we need to check this against a B climate, and we need to compare this to R, because a B climate's total precipitation cannot be greater than R. So R equals 390.96 and A equals 365.76. So the precipitation is not greater than R. So now we go to step 6. We have a B climate. Now we need to determine if it is a BW climate or a BS climate. If the total annual precipitation is less than R, I forgot what a slash symbol means. A forward slash. So if the annual precipitation is less than R/2, it is a BW. It's a desert. I looked up what the slash is called. It's just called a division slash, or an obulus if you want to be obulus, if you want to be fancy. But no, that's R divided by 2. So R equals 390.96. R divided by 2 which R is 390.96 divided by 2 is 195.48. So R divided by 2 is 195.48, and A, our average, or not average, our total annual precipitation is 365.76. So A is not less than R divided by 2. So if the total annual precipitation is less than R, which it is, then you have a BS steppe climate. Now we need to determine if the third letter is an H or a K. H is if the coldest month is greater than 0 degrees Celsius, and K is if the coldest month is less than 0 degrees Celsius. So the coldest month in our example is January. And January is minus 11.7, which is colder than, that is less than 0 degrees Celsius, which means that it is a BSK, mid-latitude steppe cold climate, because that K stands for cold. So Williston, North Dakota is a BSK climate. And that's what we figured out through this whole process. So if you go back and look at those steps and break them down, you should get a good idea of how it works. Just walk through it, give it some thought, and it should start to make sense. So now we have tropical climates, which are A climates. There's AF, it says rainforest, AW, savanna, and AM, monsoon. Tropical climate characteristics. They are located in the tropics. The coldest month is greater than 18 degrees Celsius. They are winterless. It says migrate following the ITCZ. I don't quite remember what migrates. It'll take me a minute, but that might get explained in a future slide. And they have excess moisture. There are 3 subclimates. AF, tropical rainforest, which you could think of F for forest. AM, monsoon, M for monsoon. And AW climates, which are savanna climates. I haven't thought of how W relates to savannas yet. That's going to take me a minute. So it has the climate symbol A, because it's an A climate. The largest rainforests are integral with large volume rivers. Can you make a statement as to their connection? The best examples include the Amazon and Congo river basins. AF, tropical rainforest, is monotonous and it's a jungle or the boonies. So any climate you might describe with those words are an AF tropical rainforest. Carbon sink, an area of the natural environment such as a forest or ocean that absorbs carbon dioxide from the atmosphere. Rainforests can absorb carbon dioxide, which is a byproduct of burning fossil fuels. What creates the pronounced seasons? Shifting pressure belts is the basis for the answer. In the A climates, the shifting subtropical high pressure belts and the ITCZ, low pressure, create conditions in the atmosphere for rain or no rain, thus wet and dry. The slide mentions AM tropical monsoons with a pronounced wet season, and AW tropical savanna, pronounced dry season. So I think that's related to what I just read down here. The shifting subtropical high pressure creating conditions in the atmosphere for rain or no rain. So this next slide is Dar es Salaam, Tanzania, which is the largest city and economic capital of Tanzania. On a climograph, one should include statements about economic activities, especially those that are connected to and or represent the climate. Conduct your own research to learn about mining, agriculture, urban development, immigrant labor, and remnants of colonialism. Temperate climates, sea climates. Mid-latitude climates. Let me go back here and see if there's anything in these pictures. Yeah, I'll move past the pictures. There are several interesting pictures here, but I'm not going to explain them right this minute. Mid-latitude climates. They are characterized by short-term day-to-day and week-to-week weather changes, long-term seasonal contrasts, nothing is constant, distinct seasons. Air mass conflicts occur, therefore frontal boundaries. Temperature is more important than precipitation, and they have the greatest weather variability. Humid mesothermal characteristics. Mild winters, hot summers. 55% of the world's population lives in this climate region and growing, so in sea climates. And there is tremendous agricultural potential. Humid subtropical. Characteristics found on the southeastern region of continents. Distributed moisture throughout the year. Winter cyclonic storms that produce severe thunderstorms, tornadoes, and/or snow. Marine west coast. Characteristics. Moderated by water, thus the marine effect, and there's precipitation throughout the year. Describe the distribution of precipitation that supports agriculture. There's a picture here of precipitation in Dublin, Ireland. It's difficult to see the numbers, but you can see there's precipitation throughout the year because Ireland is a CFB, CFC climate. Mediterranean, CSA, CSB. Climate descriptions characterized based on land are encircling the Mediterranean Sea. Also found on the west side of continents. There's some words here behind the pictures that I can't see, so I'm going to skip past that. But the pictures are of grape vineyards and of Cape Town, South Africa. And I believe that's another precipitation map from Greece, because these are all in Mediterranean climates. The CSA, CSB. Istanbul, Turkey. What does the land look like? There's some pictures here. One is of trees that look very dry and not very healthy. The soil looks very dry, almost sand-like, although it probably wasn't sand originally. This looks like a drought here. Let's see, there's a temperature profile, temperature and precipitation. The warmest month looks to be August with 23.2 degrees Celsius. And the coldest month looks to be January with 5.7 degrees Celsius. And for precipitation, the wettest month is December with 124, and the driest month is July with 24. Continental climates, D climates. D climates are similar to C climates, but they have severe winters. They're characterized by short-term day-to-day and week-to-week weather changes, long-term seasonal contrasts, nothing is constant, distinct seasons. Air mass conflicts occur, therefore frontal boundaries, and temperature is more important than precipitation, all like a sea climate, and greatest weather variability. But they also have severe winters. Humid microthermal. Severe winters, mild summers, very distinct seasons, good agriculture, and dominated by something that the word is hidden behind a picture. I don't remember what that word was, so I'm going to move past that. Humid continental. DFA, DWA is a long summer climate. DFB and DWB is a short summer climate. So the climates with A at the end have long summers, and the ones with B at the end have short summers. I'll have to think of a clever way to remember that. A and B. Makes me wonder, remember that show Phineas and Ferb? I wonder if they have long summers or short summers. Wonder which climate they live in. Points to make. Hot to mild summer. Long growing season, most agriculturally productive. Cyclonic storms, and distinct seasons seen in deciduous trees. In D climates, when you're looking at a chart, there's a chart here for Muskegon. This Muskegon climate graph has a sort of bell curve looking. It's where the data on the chart sort of looks like a mountain. It goes up and then comes back down like a hill. And the reason why is because you're seeing an extreme low and an extreme high charted on the data. Subarctic, DFC, DWC, DFD, DWD. Are there D climates in the southern hemisphere? The answer is no. Points to make. brief, cool summers, long and very cool winters, and pronounced continental effect. That's subarctic. Seoul, South Korea, we have a temperature profile. It looks like for temperature, their highest temperature is 25.9 in August, and I think over here in February, minus 0.8. In which Korea will you find Seoul? Astronauts flying on the International Space Station took this image of the Korean peninsula. So there's a picture here of the city lights in Korea. Kind of cool. H climates, highland climates. Now, when I started this recording, I said I wasn't going to do H climates just yet because we hadn't covered it, but by this time we have covered it in class, so we can do that in this video. Finish up with H climates. So H stands for highland climate, although it has nothing to do with the highlands of, Scotland? That is not an H climate, ironically. Highland climates. So, altitudinal zonation is a vertical classification based upon the environment, how the land is used, changes in climate, temperature and precipitation. It says T and P, which I think mean temperature and precipitation, and changes in vegetation. All of those factors make up the classification for altitudinal zonation. And there's a chart here. Agricultural and human use of the land conforms to the zones. Alright. There's a chart that shows different climates at different altitudes. So basically the other climates are not based on altitude. Highland climates are based on the altitude of the land. So we have Tierra Caliente, which is about at sea level. At sea level, you have sugar, bananas, cacao, tropical rice, coastal plains, and lowland interiors. Those are all things you find in Tierra Caliente. It's 60 degrees Fahrenheit to 90 degrees Fahrenheit, and it's at sea level. Then at 2,500 altitude, you have a Tierra Templada, which is 50 degrees Fahrenheit to 80 degrees Fahrenheit, which has coffee, wheat, cotton, beans, tomatoes, peppers, and some citrus, and the largest populations live here. At 6,000, we have Tierra Fria, which is 40 degrees Fahrenheit to 70 degrees Fahrenheit. And if you notice a pattern, it's rising in, or as you rise in altitude, it's lowering in temperature by 10, which is similar to the mountain problem, where temperature decreased as you went up the mountain. You can see the same thing here. So, Tierra Fria, potatoes, tubers, barley, plums, peaches, apples, and a large percent of land is in this zone. There's a tree line at 12,000 where there's livestock grazing. And then at 15,000, at the top of this chart here, we have Tierra Helada, which is below freezing, and you have ice and permanent snow. Tierra Caliente. Characteristics. A distinct tropical climate, think A. Continuous hot weather, think A. Along coastal plains, areas near the equator, little seasonal temperature variation. Colonization dominated much of the land used in these coastal areas. And plantation farming includes bananas, sugarcane, and bamboo. Tierra Templada. Characteristics are a cooler environment in comparison to the Tierra Caliente, coffee, corn, wheat, cotton, beans, tomatoes, peppers, some citrus, and the largest populations in South America are found in this zone. Characteristics. Let's see, which one are we on now? It says Tierra. It's probably the next one. I think the word got cut off. That's the Tierra Fria. Tierra Fria. Characteristics. Temperatures are significantly cooler, can even be frosty. Crops and natural food products are described as cool weather foods. Potatoes, tubers, barley, plums, peaches, and apples are easily grown. And a large percentage of land in South America is in this zone. So South America has H climates. Tierra Helada. Characteristics. It is too cold to grow crops, so they herd llamas in Tierra Helada, because that's at the very top, and it's freezing, and there's not very much that wants to live in those conditions as far as plants. Many live next to mines. Highest places of human habitation are in the Andes Mountains. Montane grasslands are found in areas of high altitude. The grasses provide grazing for livestock, which are the mainstay of life for people living in these regions of the world. This next slide is a picture of different climates around the globe. It's basically a qualitative climate map. So you can see this first slide is North America and South America, and each climate is color coded. And this last slide, which I think is the last slide of them all, is Africa, Europe, Asia, Australia over here. So you can take a look at those two maps, and those have the climates. So that is all the slides.